Fantastic. All right. Okay, so this is kind of where we left off on Friday. So hydrogen, we already store a lot of gases underground. Natural gas is often stored underground. There's a lot of, gas storage around the world, and also CO2 is stored underground. Okay, but the deal with hydrogen is that it's got very different properties from natural gas or CO2 or any other type of gas that you would store underground, um, including it's much less dense. It has a higher interfacial tension with water, which means that it'll have a higher capillary pressure. It has lower viscosity, and it's got a higher diffusion coefficient. So it's a little bit more difficult to contain than other gases. And I think one point that I made was if you're going to use depleted oil and gas reservoirs for hydrogen storage, you need to be careful about that, because just because the seal on those reservoirs has held hydrocarbons for millions of years does not necessarily mean that it can hold hydrogen, because it's such a smaller molecule. Okay, so one particular phenomenon that you have to worry about is how much of the pore space you can actually utilize during injection and withdrawal. And we can visualize that on this diagram. This is called a Lenormand diagram. It's named after a French petrophysicist who came up with this. And what we do is we take on the x-axis, this is the logarithm of the viscosity ratio. So this is for looking at how fluids behave when you inject them into a rock that contains a different fluid. So the viscosity ratio is the ratio of the injected fluid viscosity to the what we call the receding fluid. That's the fluid that's already present in the rock. So in the case of hydrogen storage in a saline aquifer, the injected fluid would be hydrogen, and the receding fluid would be brine, water. On the y-axis, we have the logarithm of what's called the capillary number, which is a dimensionless number that describes the ratio of viscous to capillary forces. And it's given by this term over here. We've got the interfacial tension, the contact angle, and the denominator. And then in the numerator, we have the viscosity of the injected fluid and the microscopic velocity of the injected fluid. Okay, and so that goes on the y-axis. And depending on where you fall on this diagram, you can have either stable displacement, which would look something like this. If you're injecting from the top here, you've got a nice well-defined injection front, and you're using up pretty much all of the pore space. So it's very efficient pore space utilization. But if you fall in these different regions over here, you can get different types of what we call fingering phenomena, which is where the injected fluid forms these fingers that spread out, and they result in your not being able to use as much of the pore volume. So you can either get viscous fingering if you're over in this region, or if you're down here, you can get capillary fingering if your capillary forces are very large. Okay, so let's consider hydrogen being injected into a saline aquifer at 75 degrees Celsius. So under these conditions, the viscosity of hydrogen is about 10 to the minus 5 Pascal seconds. So that's 2 orders of magnitude lower than that of water. Okay, the brine viscosity is roughly 4 times 10 to the minus 4. So if we find the viscosity ratio, it's 0.025. And if we take the logarithm of that, it's minus 1.6. Then the other thing we have to do, is so it's going to be somewhere over here. And so the point here is that regardless of what your capillary number is, you're already starting off in kind of a bad position, that you can probably expect to have some amount of viscous fingering. So it's going to be difficult to use as much of the pore volume as you need to when you're injecting hydrogen. And so the point here, like I said, is that we're always injecting very close to the point of viscous fingering. And so you can get around that by doing very, very slow injection. But but that might not necessarily be a very good idea if you're, trying to store as much hydrogen as possible as rapidly as you can. The other thing that's going to happen is that because when you've got this viscous fingering, you've got a lot of contact area between the hydrogen and the water. And so that's going to enhance the interactions between the hydrogen and the rock, which is, as we'll see in a little bit, is one way that the hydrogen can be consumed and you'll never get it back. So we need to be very, very careful about this. The other thing that can happen is if you're injecting, let's say, in some kind of an anticline structure like this, where you expect the gas to be contained up here, if you inject too fast, you can get this fingering phenomenon, and then you can actually get the gas to spill out the edges of your structure, and you're going to lose that. It's going to escape. So that's another problem with these fingering phenomena. So basically, it's a tricky problem to solve, and any underground injection is going to have to overcome this. Another thing that we have to deal with is what's called hysteresis. And those of you who are in or have taken my petrophysics class will recognize some of these slides. But this is something that happens when you inject a gas into a rock and then you withdraw it again. So we talked about capillary pressure and capillary drainage curves in the context of carbon storage, but they're also important in the context of hydrogen storage. So let's imagine that we've got a porous medium that looks like this. So the pores are all cylindrical channels, and we've got 3 different pore sizes here. So this one is just the small one. This one has the medium-sized one, and then the small one. And this one has the big one, the medium-sized one, and the small one. Okay. And so we're injecting our non-wetting fluid from the right. And we're going to draw what the capillary drainage curve looks like over here. So our initial condition is here. The entire pore space is taken up with the wetting fluid. So if I pressure up on the non-wetting fluid, it's going to try to get into these pores. And eventually, when I overcome the entry threshold for this largest pore, we're going to drain all of the wetting fluid out. And now it's going to be filled with the non-wetting fluid. So we've reduced the water saturation there. And if I keep increasing the pressure, I will then drain the wetting fluid out of the medium-sized pore. And then eventually, if I increase the pressure enough, I would drain all of the wetting fluid out of the small pore here. Okay. Now, then if you do the opposite, if you do the whole process in reverse, where you reduce the pressure of the non-wetting fluid, it would just follow the same steps exactly in order. And so go exactly back down the same capillary drainage curve. And the reason that happens is because these pores all go in order of decreasing size from right to left. So there's no mechanism that would trap the non-wetting fluid in there. We talked about this again for CO2 storage. So real rocks have more complicated pore networks, and as a result, when you do a drainage and then follow that with an imbibition step here, you don't take the same path on the way out that you did on the way in, and there's always going to be some amount of non-wetting fluid that gets trapped, that gets left behind. So if you're thinking about hydrogen, this amount of hydrogen, you're going to inject that, and you're never going to get it back, okay? And then the other thing that happens is if you're doing seasonal storage and seasonal withdrawal, depending on what the water saturation is when you start your injection and withdrawal cycle, you can end up at different positions in between these curves. And so, we've done some investigation about how much hydrogen you actually lose as a result of different seasonal injection and withdrawal cycles. And it can be as much as 30 or 40% of what you've injected, just you'll never be able to get that back out. So that really is going to have a big effect on the economics of underground hydrogen storage if you just have to count on a certain amount just being left down there, forever. So that's one issue. Now, there's been some work done looking at how the hysteresis will evolve over multiple injection and withdrawal cycles. So here's some simulation work of capillary drainage curves over 5 injection cycles in a Berea sandstone sample. And they're predicting that there's going to be very limited hysteresis. But there's other studies that have shown, including the work that we've done in my group, that have shown that you will have actually a very large hysteresis. So it's still kind of an unknown thing. We don't really have any field experience at this point that's going to tell us whether or not this is going to happen. So to me, this is kind of one of the larger deals that we need to figure out, or someone just has to go out there and test it, and we'll figure out, how much you're actually going to lose. Okay. Now, another thing you have to think about is that you will typically use what's called a cushion gas that sits below your hydrogen. And this allows you to have more efficient release of the hydrogen during withdrawal cycle and more efficient injection during your injection cycle. So this is gas that you inject and you never expect to get back. And so that's different than the trapped hydrogen that you don't get back. This is cushion gas. A lot of people are looking at the use of methane as a cushion gas because it's cheap, it's denser than hydrogen, so it'll sit below it. But you can also use things like CO2, and we actually have done some work in my group where we've suggested that actually using hydrogen as its own cushion gas may, again, be something that could work better than some of these other gases. But again, this is another thing where having some operational experience will allow us to make better informed decisions about cushion gases. Okay, so there's not just the residual trapping and the hysteresis stuff that is going to lead to consumption of your hydrogen. Microbes love hydrogen. It's a very good source of electrons, and that can be used to produce energy. And when microbes consume hydrogen, you're losing your hydrogen, which is bad, but also they can produce hazardous chemicals that need to be separated out from the hydrogen that you do produce back to the surface. A good example of that is hydrogen sulfide. So if you have sulfur-reducing bacteria, they will produce hydrogen sulfide, and that can be very expensive to remove from the produced hydrogen stream. Another one is methanogens will create methane. So you're turning your hydrogen into methane. That's not a good thing either necessarily. So you have to be very careful about this. And these microbial reactions can be very difficult to predict because you have to know what microbial assemblage is present in your reservoir. And without doing very detailed analysis, that can be a very difficult thing to predict. So I'm going to show you some data illustrating this from one of the few field examples of hydrogen storage that have been done so far. This was a project in Austria that was done over the course of 2016 and 2017, where they injected hydrogen into a depleted gas field. So they've got a couple of wells, so 4 wells here. This is showing the map of the structure, showing that you've got this closure up dip here, which will trap the hydrogen. And so they had electrolyzers at the surface that generated the hydrogen, and then they pumped it underground into the reservoir. And so they did a very small amount of hydrogen. It was mixed with natural gas. And so they did a 3-month-long injection cycle, 4 months of just being shut in, nothing happening. And then they produced the gas over the course of 3 months. So the nice thing is that they did a very good job testing all the materials that they were using downhole and at the surface to make sure that there would be no corrosion issues. So that was good. They also did a good job testing the properties of the reservoir rocks. So they didn't have much in the way of fluid rock interactions. So that was a good thing. But one problem they had was with microbial consumption of the hydrogen. And so they did tests for the amount of DNA and the amount of RNA that was present in the fluids at a couple of different depths. You can see 1,200 meters and 1,350 meters within their borehole. RNA in particular is important because that tells you something about how much microbial activity is down there. The DNA just tells you that there are microbes, but the amount of RNA tells you that they're, whether or not they are active. And they specifically tested for methanogens, and they found that they had, significant activity of methanogens in the reservoir. And what the methanogens do is they take CO2 and hydrogen, they make methane and water. And here's the thing. The natural gas that they used had a very minuscule amount of CO2, 0.2% by volume. But that was enough to get the microbes going and start consuming the hydrogen. So you have to be very careful with your injected fluid chemistry and also understanding what microbes you have before you start injecting. Okay, so the takeaway here is that you can reduce geologic risk, you can do materials testing and reduce the amount of corrosion that you're going to have, but microbes are very difficult to predict, and you have to have a very detailed understanding of what microbes are going to be down there. So right now, there's still a lot of challenges and uncertainties associated with underground storage, including fluid rock interactions, viscous fingering, choice of your cushion gas, microbial reactions, mineralization, all kinds of stuff. So it's a complicated system, and it's still an area of active research. Okay, so that brings us to the end of underground hydrogen storage. Any questions on this? No. Okay, fantastic. Let's okay, so that's it for that. So now we're going to jump into the last bit on hydrogen. And this covers the topic of using hydrogen. So, we've talked about making hydrogen, we've talked about transporting and storing hydrogen, but what are you actually going to do with it? So you can, the couple of uses here are basically you can use it as a source of energy, or you can use it, we'll look at a couple of cases where you can actually use it as a chemical rather than a source of energy. And so we'll see where that goes. So to get energy from it, you can either burn it or you can use it in a fuel cell. So let's talk about that real quick. So this is a generic gas turbine. So this is what's used in a typical combined cycle natural gas plant. So the air comes in here, it gets compressed, it gets mixed with the natural gas, which spins the turbine, and then the exhaust comes out the other end. So it's a pretty simple system, but there are a couple of modifications that you would need to make if you wanted to burn hydrogen in a turbine like this. And so it's got different properties compared to methane, including the lower energy density and the higher flame temperature. And so if you want to retrofit a gas power plant like the one across the street here to burn hydrogen, you first of all, you need the equipment to be able to handle higher flow rates, because remember, with hydrogen compared to natural gas, it's not the volumetric flow rate, it is the energy flux. And so to get the same energy flux coming through the pipe, you need to flow faster because the energy density is lower. The combustors need to be designed a little bit differently because of the faster flame speed of hydrogen. So, sometimes when I'm at home and I'm cooking on, we have a gas cooktop at home, I think about what if that flame went down into the pipe and started burning all the gas that's in the pipe? That would be a problem. And, the reason that doesn't happen is because the nozzles on the combustors on anything that burns natural gas are designed such that the gas comes out at the same rate as the flame speed or faster than the flame speed. And so the flame is not able to back propagate into the pipe. You'll have to design that differently for hydrogen because the flame speed with hydrogen is faster. And you can do that, it just takes a different nozzle size. Yeah, question over here. Oh gosh, that's a really good question. I don't remember off the top of my head. It's not like orders of magnitude faster. It's like small integer multiple faster. It's no, it's outside that. So you do need differently designed nozzles. Let's see, because hydrogen leaks more easily than methane, you need to change all of your seals and welded connections and stuff to make sure it's not leaking. And then speaking of leaks, you need more advanced leak detection equipment. And the reason for that is because it burns at a lower concentration in air, so there's more of a safety hazard. And the flame is nearly colorless. So here's a good comparison. This is a natural gas flame. It's that familiar blue color. And then this is a hydrogen flame. You can see that you can barely see it. So there's a little bit of a safety issue there. And so we've talked about natural gas blending with hydrogen. And I think we've seen this figure before, but up to about 30% hydrogen, typical gas turbines can handle that without any type of retrofitting. But this was an interesting paper from a couple of years ago looking at the cost of upgrading gas turbines depending on how much hydrogen you want to mix with it. So if you go up to say 50-50 mix, you have to spend an extra 7% of your capex in building the plant to upgrade gas turbines, or you can just buy new hydrogen turbines, which are much more expensive. So, it's there is a cost associated with this if you want to retrofit different, different amount for different. What am I trying to say? If you want to retrofit a power plant, that's what I'm trying to say. Okay, but I think I've made this point before. But this is a situation where we should not let the perfect be the enemy of the good. And any amount of hydrogen blending will reduce the carbon intensity of electricity generation simply because you're taking some methane and you're replacing it with hydrogen, okay? And so this is a plot. The y-axis here is the relative carbon intensity versus the volume percent of hydrogen that you're mixing with natural gas. And so, even at 30%, which is what you could do in a regular natural gas power plant, we read up here, you've reduced the carbon intensity by about 10%. You're down to 90%. I mean, that's a good thing, right? I mean, obviously, we'd like to reduce that a lot more, but some is better than nothing. So, here's another study from Dr. Weber's group over in mechanical engineering. So if, let's see, if you look at the existing hydrogen pipeline network, which is mainly centered around Houston because it's used for the chemical plants down there. So if you took all the gas power plants that are within 5 kilometers of those existing hydrogen pipelines, okay, and just blended 5% hydrogen in there, the reduction in CO2 emissions would be equivalent to taking about 386,000 cars off the road. So, you know, that's, or then at 30%, you're taking about 2.3 million cars off the road. So, you know, that's, again, that's a good thing. So I think, you know, people sometimes like to hate on hydrogen blending because you're still using natural gas. But I mean, you know, it's something. Come on. Okay. Now, the other way that you can get electricity with hydrogen is by using a fuel cell. A fuel cell is basically an electrolyzer that's being run in reverse. And so you combine hydrogen with oxygen and you produce water. And the way it works is that you've got an anode and a cathode. And so you've got flow of protons and electrons that gets the hydrogen gets separated into those by a catalyst. And you get an electrical current that flows across your anode, from your anode to your cathode, and it generates electricity, which is then carried through this electrolyte. Okay, so it's a pretty straightforward process. The problem is that a single fuel cell typically generates about 1 volt. So that is less than a AA battery, right? AA batteries are 1.5 volts. So you need to combine a whole bunch of fuel cells together to generate higher potentials that could be used to generate electricity at a useful scale. So there's a whole bunch of different types of fuel cells, and they can be stacked to give you different amounts of power that you're generating. You know, as an example, you know, a solid oxide fuel cell, you can go from kilowatt to megawatt scale. So that's something you could, you know, maybe use at, you know, for a utility scale installation. One of the issues with a lot of these high power fuel cells is that they operate at very high temperatures. So solid oxide fuel cell, you're at 500 to 1,000 degrees Celsius. That's pretty hot. And also they have varying levels of efficiency. So, you know, there's various applications for these, but, you know, utility scale, you're looking at either the molten carbonate or solid oxide types of fuel cells. There's a lot of work being done on fuel cells right now because there are, you know, a lot of challenges associated with this. Some of the catalysts are quite expensive. Some of the electrolytes are complex or hazardous or made out of critical minerals like lithium, yttrium, zirconium. So, you know, again, these are things you have to think carefully about. So, you know, there's no perfect fuel cell at this point, but, you know, this is a way of making, you know, energy from hydrogen without having to burn it. Okay, so for power usage, if we look at what you can get out of these, so an electric car, plug-in electric car is about 7.3 kilowatts. So over here, if we come back, you know, these ones that operate at the kilowatt scale, you could, you know, power an electric vehicle off of those. Fuel cell cars, there are hydrogen fuel cell cars, are, you know, about 100 kilowatts. But, you know, if you start thinking about powering, for example, a steel mill, you're at hundreds of megawatts. Same thing, utility scale. So Austin Energy, on average, 700 megawatts. And then all of the ERCOT grid back in August of 2023, 85 gigawatts. So scaling up fuel cells to meet that kind of demand is still a bit of a challenge, but we may see more of this in the future. Okay, the other thing we have to think about with these fuel cells is the catalysts, okay? A lot of them use platinum. That is expensive. And so if you're deploying these at utility scale, that's some money you have to put in. There's these chemicals called transition metal nitrides, including cobalt nitride. So, okay, we can start using cobalt for this. Remember the thing with cobalt. Let's see, Washington University in St. Louis, another cobalt-based catalyst. So, there's some problems there, but there are some other groups that are looking at iron-based catalysts and that sort of thing. So, obviously this is an area of active research. Oh gosh, I haven't been learning this. And an area of active research that a lot of people are looking at, and that's where that and other other parts of the fuel cells are where a lot of effort is going right now. One other kind of side benefit of hydrogen fuel cells is that they operate at high temperatures, and that's not a temperature that you have to give them. That is a temperature that they generate as a result of their operation. And so that produces waste heat that you could actually use for something. Actually, I think I've made this point before. Waste heat in general from energy production is a tremendous opportunity because a lot of it is just lost. So if you can capture that and use it for something else, that can be a very good thing. So, for example, you could use this for like hot water generation if you're running your house off of a fuel cell. So, stuff like that. That's called combined heat and power. So, that could be combined with large-scale fuel cell usage. Okay. Now, another use of hydrogen is, and this, you're thinking about your final project, this might be something that you can consider. How am I going to use, could I use hydrogen for something here? And there are these industries that we call hard to abate industries. And these are industries that emit a lot of carbon dioxide, not because of energy consumption, but because of the actual processes that they use. And so examples of this are steel manufacturing and cement production. And so we'll talk about how hydrogen could be used to abate some of those CO2 emissions. Okay, so carbon dioxide, cement is one of these industries. And the way the cement manufacturing process works is that you start off with your raw materials, which are generally limestone, sand, clay, and iron ore, and maybe some other additives that you put in there. And they are heated to a very high temperature, about 600 degrees Celsius, and run through a kiln. Now, what happens in the kiln is there are some chemical reactions, one of which is the decomposition of the calcium carbonate that's in the limestone. And it produces this material called lime, which is calcium oxide, and releases CO2. Okay, so you cannot make cement without this reaction happening, and it just generates CO2. The result that comes out at the end of the kiln here is a material called clinker, which is ground up to make the actual cement powder. Per metric ton of clinker, you generate 842 kilograms of CO2. So that is a pretty large amount of CO2. And part of what goes on here is you're generating the CO2 from this process here, but also you're using energy to heat the kiln. That's about 45% of that 842 kilograms. So if you use hydrogen to heat your kiln, there goes 45% of your CO2 emissions. And then maybe you can capture the rest or, something like that. I did read an article recently, if somebody's looking for a news item, I did read an article about advanced cement manufacturing that does not use this step at all. And so you're not producing any CO2. And unfortunately, I don't remember what they were doing instead, but it was something else. So, that's another possibility. But, hydrogen could be part of the solution here for cement. Okay. Now, with steel manufacturing is about 7 to 9% of all anthropogenic greenhouse gas emissions. So it's a huge contributor to CO2. Per metric ton of steel, you are producing 1.85 metric tons of CO2. So you're producing more CO2 than steel, which is crazy, okay? Now, the way it works is that you take iron ore and you put it through a blast furnace, which changes the chemistry of the iron ore into just pure iron. So you're reducing it. And that the oxygen that's produced as a result of that reacts with the coal and it emits CO2. And then it goes through an oxygen converter that converts it to steel. So there's a couple of things going on in here. So one is that the chemical reactions in the blast furnace produce CO2. You're also using energy to heat the blast furnace and also the oxygen converter. So there's a couple of steps here where you could use hydrogen. You can certainly use it as a fuel source for heating these things. But there's actually another place where you can use hydrogen in the chemical reactions that happen here. So this is an illustration of your typical blast furnace process. So you take your iron ore and you put it through, you mix it with these pellets of usually coal, and then you run that through the blast furnace, and that emits CO2 both from the energy and from the chemical reactions. And then the oxygen furnace also emits CO2. So if you use hydrogen as your fuel source, and then the other thing is that you can use hydrogen. And remember, we talked about syngas before, right? That's a mixture of carbon monoxide and hydrogen. You can use that to reduce the iron oxide in the blast furnace, and that will generate hydrogen and water rather than CO2. And so that, and at the end of the day, you're still producing steel. It's still steel. There's nothing different about it. It's just the chemical reactions that you've used to get there are a little bit different. So that's another possibility. Okay, I got so excited about decarbonization, I almost missed that it's the end of class. So thank you all for coming, and I'll see you all back here on Friday.